Now, I am moving on to next chapter, potentials. So, I don't know whether you observed or not. There is a potential chapter, scalar potential. We call this one scalar potential because in magnetostatic, vector potential is going to come. And the similar potential chapter doesn't exist in magnetostatics. Is that okay? In electrostatic, he has chapter electrostatic, chapter potential, chapter electric field in matter. In magnetostatic, he has chapter magnetostatics and magnetic fields in matter. Why not magnetic vector potential? Isn't it? I think I told that one. Now we will go in a different way, okay? Del dot B equal to 0 always. Okay, we shall prove this one after defining Biot-Savart law, outcome of Biot-Savart law. Once it is true, that I can write as B as del cross A. Now I can calculate A and then I can calculate B. What is the use, isn't it? A is also vector, B is also vector. Isn't it? But this formalism is very rich. Again, Griffith's word. Okay, what is that? Del cross E is equal to 0. That's why E can be written as negative gradient of potential, and you can find one scalar. So, and you can take gradient to find vector. But here you have to find vector. That's why that formalism is not that rich. Okay, we can find scalar. We can have scalar integration. For finite charge distribution, I have written like this: 1/4 phi epsilon naught integral of dq by r, like that. Am I right? So it was very simple, remember. So compared to electric field integration, it was very simple. So that's why this formalism is very rich, and again you can solve many equations. So that's why we have a chapter on this one. That's a potential chapter, third chapter. Okay. Now, any question? Where? No, that's very later. Okay, very later. After electrodynamics, we shall talk about gauge transformation. I mean, this potential formalism is not unique. Okay, that will allow, that will give us some freedom. That is gauge transformation. Okay. Now, whatever we have until now, it was electric field, which was written 1/4 phi epsilon naught integral of rho of r prime vector d tau prime divided by r square into r cap. Am I right? So then our potential, this was very difficult. Am I right? You need to take components of individual one and you have to do that integration. But this was very simple. I hope you got some experience now. 1/4 phi epsilon naught integral of rho of r prime d tau prime divided by italic r. Isn't it? It's the potential at r. Potential at r. Am I right? At a position in space. So actually, for a again, these two were the formalism we had, or formula we had. Now, how I can relate them? Electric field is equal to negative gradient of potential. Is that okay? If you now, so potential, how do you find charge density? I mean, del square V is equal to minus rho by epsilon. Right? Del square V equal to minus rho by epsilon. Actually, this is a solution of this equation. You might have given in appendix, okay? This whole thing is a solution of this one by assuming potential vanishes at infinity. This is only for finite charge distribution. For finite charge distribution, you can assume potential vanishes at infinity. Again, whenever you solve differential equation, you need boundary condition. So for finite charge distribution, by taking potential vanishes at infinity, you can take this is the solution of this one actually. But that not that straightforward, okay? But in most of the case, whenever wait a second. At all points where at all regions or regions where rho equal to 0. in regions where rho equal to 0, what would happen? Del square V is equal to 0. Am I right? We call this as Laplace equation. And most of the case, we are interested to find our potential in the region where there is no charge. That potential that is created by charge somewhere else. We need potential and field somewhere else, not in the region of charge. So then usually this Laplace equation is followed in that region where there is no charge, but fields are created by the charge somewhere else. Okay. Now again I asked one question: if all the regions satisfy same equation, then potential is same for all charge configuration? No. What is the difference then? Boundary condition is the difference. Boundary condition is what you call unique for one charge configuration. Is that okay? So, but this equation remains same for all empty space. Charges are somewhere. For all other empty space, you got this Laplace equation satisfied. Now we shall see what are the properties of this Laplace equation. Okay, what are the properties of Laplace equations? I mean, what are properties of the function which satisfies Laplace equation actually? Okay, wait a second. So, del square V is equal to 0. We shall see property of that potential which satisfies Laplace equation. Property of the potential which is in any empty space. In any empty space where there is no charge. Again, we call solution as harmonic function. I hope you know that one. Okay. Solution of Laplace equation is called as harmonic function. Name. Okay. Now don't think of simple harmonic motion whenever I say harmonic motion, harmonic function. Okay. Solution is named as harmonic function. They may use that word. Now let me take 1D. Okay. Let me take one dimensional. One dimensional. What would happen to your Laplace equation? What is Laplace equation in Cartesian coordinate? Rho square V by dou Z square. Can you see this part? Yeah. What is Laplace equation in one dimension? D square V by dx square. One dimension means potential. If it is a function, it should be function of x alone. Am I right? When you substitute that one, so what would happen? dv of x divided by dx square. You don't have to write partial derivative for only one variable is equal to 0. Okay. So now shall I solve this one? Integrate this one. What would happen? Integrate with respect to dx. This means d by dx is equal to constant. Am I right? D by dx is equal to constant. Now let me put that d by dx equal to m. Is that okay? Again integrate. dv is equal to m dx. When you integrate, v is equal to mx plus c. What is this one? Straight line, isn't it? Yeah, we got a straight line passing through some y-intercept or something. Am I right? V of x as a function of x. That's a straight line. Again, what are the properties of straight line? It is straight, isn't it? What are the properties of straight line? Now look at here. Again, properties are, am I right? This is c, slope equal to m, y-intercept. Again, unless you define that initial condition, you can't find these two. Is that okay? That's why this is the general solution of Laplace equation in one dimension. We have to observe two things here. Okay, write down. First one is, look at here, v of x is average of v of x is average of v of x plus a and v of x minus a. Now you have to ask how that happens. That happens for all straight line equation. Or even you can take v of x plus a, v of x minus a, using this equation, divide by 2, you will get v of x. You got solution now, isn't it? So take, this is v of x. Okay, this is v of x. Write v of x plus a, write v of x minus a, divide by 2, you will get v of x. Is that okay? V of x equal to, you can show this one, v of x equal to half of v of x plus a minus v of x plus v of x minus a whole divided by 2. That's the meaning of average, am I right? So now for any A, write down like that. For any A, any arbitrary A, however small, however large. Okay? So now what do you mean by that one? Potential is always average of its neighborhood. I mean, potential at any point is average of the potentials from its neighborhood actually. Is that okay? Potential at any point, the x is arbitrary point. It's always is equal to average of the potentials in its neighborhood. Can I say like that? So that's why he says Laplace equation is a kind of averaging instruction. You keep on average, I mean, you have to develop the potential curve in such a way that this happens. Are you getting my point? You have to, that potential curve should evolve in such a way that, I mean, next point, again, you have to evolve next point in such a way that, so that again, averaging should happen. That is the observation for one dimension. Obviously, one dimensional is very less important. Okay. So, but this will happen. What is the second one you observe? What is the second one you observe? Yeah, write down here one more sentence. Laplace equation is a kind of averaging instruction. Laplace equation is a kind of averaging instruction. Okay? That's how it evolves. Curve evolves actually. So second one, Laplace equation tolerates no maxima or minima. That's a property of the straight line. Where is a minima? At minus infinity. Where is a maxima? At plus infinity. Isn't it? Laplace equation tolerates no local maxima or minima. Write like this. Laplace equation tolerates no local maxima or minima. Comma, extreme value of the potential must occur at endpoints. Extreme value of the potential must occur at endpoints. Either case. So that is the property of straight line, am I right? There will be, so straight line is something, it's not a curve. So it will not happen like this. There will be no maxima or minima. Extreme values will happen only at endpoints. Okay. Again, this is the one dimension problem. Now what we do here is in two dimension, it will be partial differential equation. Am I right? If you take 2D, what would happen? Del square V of x comma y is equal to 0. Am I right? That becomes dou square V by dou x square plus dou square V by dou y square is equal to 0, isn't it? Now you have to go for variable separable to solve this one. You need boundary condition like that, isn't it? But what we do here is we are going to extend our argument, earlier argument. We had one dimension. What we got, potential was average of its neighborhood. Potential at any point is equal to average of the all potential from its neighborhood. Okay. So now that's the one point. Other point is there will be no local maxima or minima. All extremum points that will occur at end points or infinity usually. Okay. So now we shall take those two ideas. We can apply this one because this again extension of that problem in the two dimension, isn't it? So now look at here. Actually, we can draw this kind of two-dimensional potential. Is that okay? Just like a hill problem that we have taken. Height of the hill as a function of x and y, isn't it? So now we can just draw this v of x as a function of x and y. You can draw it like this, isn't it? But three-dimensional potential cannot be imagined, isn't it? So, but two-dimensional potential, we can draw it like this. We can represent that one. Is that okay? So now, since the potential suffers no local maxima or minima, is that okay? And potential is a kind of averaging instruction. I mean, it's a kind of averaging kind of thing, or potential at any point is average of its potentials around its neighborhood. Is that okay? Now again, how to get those ideas? If you try to apply all of those, so he has given one interpretation. Suppose I had a box, okay? I had a box, so cubical box. What I do here is I am going to cut down that box like this. I am going to cut down the box like this. I had a cubical box. I am going to cut down the box in some arbitrarily shape. Is that okay? In some arbitrary shape. Now what I do here is I am going to take one rubber sheet, very thin rubber sheet, and I am going to just tie that rubber sheet, or I am going to paste that rubber sheet. I am going to just drag that rubber sheet on this one, and I am going to paste that one using some gum or something. Is that okay? So then whatever the structure, whatever the surface you get of that rubber sheet, that will be the possible potential. You have to stretch that one. You have to stretch and you have to paste it into its edges. Is that okay? Then whatever the shape of the rubber sheet surface, that is the possible potential. It will never have any maxima or minima. Is that okay? It will never have any maxima or minima. You can just check it out. Or you can think like that. You can think like that. Suppose if you keep, I mean, usually now when you put that rubber sheet on the earth's surface, now that is the surface, that surface again, that is the surface of potential, am I right? Different height, different position. Again, our what you call gravitational potential will also not suffer any maxima or minima, remember. Is that okay? Then if you just put any small ball, it will slide off actually. You can't keep any ball at rest using this kind of configuration. On that rubber sheet, you can't keep any ball or particle at rest. Is that okay? There will be no dip like this. There will be no three-dimensional dip like this, so that you can keep that ball at rest. Is that okay? So when you keep ball anywhere, it will slide off. Is that okay? It will slide off. So this is a possible potential. In case of two dimension, we can imagine, we can even interpret, we can demonstrate also. Is that okay? So now again, the same two sentence we are going to write in case of two dimension. But the first sentence, it was a averaging kind of thing, am I right? Potential at any point is average of its neighborhood. Now what I do here is, I am going to take one point on x-axis, okay, xy plane. Is it? Point on xy plane decides the potential now. So now what is the neighborhood of that point? Now you are on a plane. What is the neighborhood? Neighborhood becomes a circle. Is that okay? Now collect potential due to all points in the circle. Let me take radius of the circle is r. Can you imagine? I have a point on xy plane. Now let me draw a circle. Now circle is a neighborhood of any point in a plane, isn't it? So now what I do here is I am going to find potential at all of these points. That will be, you have to extend like this actually. You have to extend upward, because upward surface is my potential, am I right? I mean, this height is my potential. So then it may be like this. Is that okay? When you just extend this one, Your potential may have this kind of values, isn't it? Can you just imagine when you just take this one, when you just take the projection on the plane, you will get this kind of curves, isn't it? That will not become circle. Neighborhood is a circle when you collect all of those potential values, okay, on that neighborhood. Let me just write that one like this: circle, potential on the circle, okay, potential on the circle, V into TL, and I need average. This is a summation of all potential in its neighborhood. Am I right? In case of one dimension, neighborhood was only 2 points, 1 point after, 1 point before. You added that one. Now neighborhood is a circle. You added all potential around the circle. Now you have to divide by something. What you are going to divide to find the average? Y area, circumference. You are not adding the potential in the surface. Remember, you are adding the potential on the closed curve. So 2 pi r. This is the average. Okay. So potential at any point is equal to average of its potential in its neighborhood. Potential at any point is equal to average of its potential in its neighborhood. What is this circle now? Circle which centered at x comma y. This was my x comma y. Just write down. This was my x comma y. That center was my x comma y. Take any circle which centered at x comma y and integrate your potential and divide by 2 pi r. That's a kind of average. And write down the sentence. The value of v at x comma y, the value of v at x comma y is average of those around the point. Is average of those around the point. Those means potential. Okay, is average of those around the point. Second point. Yeah. Two-dimensional. Where? No, yeah. You can, I mean, for average, for finding the average. No, actually, neighborhood means we have taken for one dimension. Suppose this was x, we have taken x plus a and x minus a. Am I right? Those are equidistant. Those points are equidistant. Like that, if you collect all point which is equidistant from a point, this will become circle. That's how we say that's a circle. Square, I don't know, it looks good for a neighborhood. Is that okay? Circle is a neighborhood. Is that okay? And it can be however small it can be. So it can be as small as possible. Is that okay? Now, so next one is, so second one. Potential has no local maxima or minima. Again, the same sentence, write down. Potential has no local maxima or minima. Remember, as long as it satisfies this one, okay? As long as that satisfies this one. We are talking about that region, the region where Laplace equation is satisfied, okay? Don't forget, initial one. Yeah, potential suffers no local maxima or minima. All extrema should occur at the boundaries. All extrema should occur at the boundaries. But we can't draw three-dimensional potential, only we can state something. dou square v by dou y square, dou square v by dou z square is equal to 0. Okay, let me write the same two sentence. Okay, potential. Now, if you now potential is a spatial variable. I mean, potential depends on x, y, z. Am I right? Now, for a point in space, what is the neighborhood? It's a sphere now. Is that okay? So now what I do here is I am going to take suppose v at r. Let me write like this: potential at any point, any position in space. So now take a sphere which centered at this r, this point. Remember, because that sphere should be centered at this point. That sphere should be neighborhood of this point. That's why you have to take sphere with this center, not center at the origin. Remember. Are you getting my point? You have origin somewhere here. Is that okay? You have some point in space. Okay? Now what is the neighborhood? Neighborhood is a sphere now. Am I right? Neighborhood is a sphere of radius capital R. Let me assume like that. Okay? Neighborhood is a sphere of capital R. Now what you have to do, you have to integrate your potential over the sphere. Sphere means spherical surface, not volume integration, okay? Surface, you have, that surface is neighborhood now of that point at the emitter. Is that okay? Now if you find all of those potential over its, over the surface, then what you have to do, you have to divide by surface area. Isn't it? You better put sphere here. So potential at any point is average of its neighborhood. Yeah, can you write on sentence? The potential, the value of potential at r vector, the value of potential at r vector, is average of v over spherical surface, is average of v over spherical surface of radius capital R, centered at small r vector. Centered at small r vector. Small r vector means that's the position vector of a point in space. Centered at small r vector. That's what we have written here. Okay. Again, what is the next sentence? Potential has no local maxima or minima. Write down. Last one. Don't we will not go for 4 dimensions, isn't it? Potential has no local maxima or minima. All extreme values must occur at boundaries. Yeah, he has given proof for this one. Can you just do that integral? Yeah. Quickly, look at here. Let me quickly go through this proof. And I think I haven't solved any of the spherical integral. We used Gauss law earlier, do you remember? We haven't solved any spherical integral. This is one of them, okay? So, to do that spherical integral, I'll take, this is the point of interest. I'm going to place my Q here. That's the best idea. Isn't it? I'm going to find what is the potential at this point. Is that okay? What is the potential at this point? Suppose it is at a distance z over here. Z cap, x cap, y cap. What is the potential at this point now? So potential at origin. 1 by 4 pi epsilon naught. So Q by Z, am I right? That is the potential at center, at at O, let me write like this, potential at 0 actually, 0 vector, null vector, isn't it? Now let me calculate that one, let me show that one. I am going to take, what is the neighborhood of this point? Now it's a sphere. To take little bigger sphere. Charge q at a distance z on the z axis. Is that okay? So now, look at here. This is my sphere of radius capital R. Okay, this is my sphere of radius capital R. I will take now what I do here is, now I have to integrate my potential over this one. Now I have to define potential at all points over the surface. Am I right? So now take small patch of area. Let me call it as dA. Okay. Now this is at a distance italic r, because you need to find potential at this point, isn't it? From source point to field point. What is the vector? Italic r. Okay, now let me take this one as your capital R. This is capital R, am I right? So from center to point on the surface, that's capital R. So this is theta. If you take projection, that will be phi. Now what I do here is, I'm going to take one vector, okay? I'm going to take one vector where we can take z minus r. Yeah, let me take one vector in this direction, okay? Usually we take italic r from source point to field point, am I right? Then let me take one more vector along this direction, okay? So this vector is z into z cap. This distance is z, it is placed at a distance z. What is this vector? R into r cap. This is italic r vector. Now I can write italic r vector as r vector minus z cap. Can I write like this? Or r cap minus, yeah, r cap minus z cap. Am I right? So what is the angle between r cap and z cap? Because I need magnitude. Theta. That's a theta that is defined with respect to r and z cap. Am I right? So now if you take r square dot product with itself, what would you get? R square plus z square minus 2rz. Cos of the angle between them is theta. So italic r is equal to root of r square plus z square minus 2rz cos theta. Now potential on the surface 1 by 4 phi epsilon naught q by this italic r, isn't it? Now you have to surface integrate that one. Now you have to surface integral that one. I mean surface integral of VdA. Okay, surface integral of V, or let me just find average of the potential. Am I right? This is average. What is average? 1 by 4 phi r square integral of 1 by 4 phi epsilon naught q by italic r into dA. What is dA? What is this dA? That should be your dA along r cap. Am I right? Magnitude, but here the vector will not come. What is that one? R square sine theta d theta d phi. Small r equal to capital R on the surface, isn't it? R square sine theta d theta d phi. That was your area vector that is along r cap direction. Am I right? But you have to take only magnitude here. But you are referring to the same surface, remember. Okay. We are referring to the same area, but we are not taking area vector here, okay? So now 1 by 4 phi r square, 1 by 4 phi epsilon naught, q by 4 phi epsilon naught, q r square by 4 phi epsilon naught. Italic r contains theta, am I right? 1 by root of r square plus z square minus 2rz cos theta into sin theta d theta. Theta runs from 0 to phi. Theta runs from 0 to phi. Phi runs from 0 to 2 phi. Phi integral is 2 phi. Now you have to do it by substitution. Or I think you can substitute the whole these things as some t, am I right? So that sin theta d theta will be dt, isn't it? When you do that integration, let me do it directly, okay? So because let me save some time, q by 4 phi epsilon naught, okay, 1 by 4 phi r square, q by 4 phi epsilon naught, 1 by 4 phi r square, q by 4 phi epsilon naught, one more r square was there, am I right? Yeah, that I have taken outside. Somewhere here also, I think 2rz cos theta, rz will come out. Can I write next one? Do it yourself, okay? Let me write next step directly. Q by 4 phi epsilon naught, 1 by 2 z r. Q by 4 phi epsilon naught, 1 by 2 z r. After integration by after integration, okay? Root of z square plus r square minus 2 rz cos theta runs from 0 to phi. Runs from 0 to phi. Is that okay? Now that will be 1 by 2 z r, 1 by 2 z r, z plus r minus z minus r. Here I played one small trick. At pi, cos pi is minus 1, z square plus r square minus 2rz cos theta. Am I right? At lower limit, 0. So that is 1, I have written z plus r the whole square. Other, I have written z minus r the whole square. Why I can't write r minus z the whole square? Upper limit, okay? Lower limit, now look at here. If I had written r minus z the whole square, my answer would be different. Check that out. Z minus r the whole square is same as r minus z the whole square, isn't it? I too don't know how to explain this one, okay? Tried many times. If I keep that z minus r, what would happen here is, yeah, z will add up, r will get cancelled. Z will cancel, am I right? Z minus z, r will get added, and 2r will get cancelled, you will get that answer. But if you write it ulta, r will get cancelled, isn't it? Now I don't know why we have to write like this. Both of them will not give the same answer. Are you getting my point? Are you getting the trick? Q by 4 phi epsilon naught, 1 by 2 z r. So this is z plus r. This is z minus r. Think over it. Try to answer this question. Okay? Z got cancelled. 2r. Am I right? So 2r got cancelled. This is 1 by 4 phi epsilon naught q by z. What is this one? Average of the potential over the spherical surface which is centered at the origin. That's equal to this one. That is equal to potential at the center. Yeah, try to answer this part, okay? Z greater than R. Whatever, it doesn't matter if it is squared. Anyway, we square, then we can take root, am I right? That's correct, okay? Z greater than R, am I right? Here Z is greater than R. But anyway, when you have something in square, you don't have to worry to take root. Now, this is the situation. Again, we can apply all of this only when in that region del square V equal to 0. Is that okay? In the spherical surface, whatever we have taken, the neighborhood, whatever we have taken, in that neighborhood, one more charge should not come. Then Laplace equation will not be satisfied. Then this is not true. Is that okay? So that is the next problem. This is asked in JEST exam, I think. Problem number 3.1. So problem number 3.1 or first problem, okay? Problem number 3.1 or first problem. Find the average potential over a spherical surface of radius r due to a point charge q located inside. Same as above, z less than r. Yeah. For z greater than r, you have to write z minus r the whole square. For z less than r, you have to write r minus z the whole square. Then you will get other answer. Are you getting my point? Can you give pure mathematical explanation for this one? Is it okay? Because of the fact that, as he said, so as somebody said, isn't it? Z should be greater than, Z is greater than R here, isn't it? Z greater than R, that's why you have to take Z minus R the whole square. Okay, now what I have here is, I have charge Q here. Now my surface is like this. I am going to find average over the surface like this of radius capital R. Now my surface is, my radius is greater than, this is Z. This Q is placed at a distance Z here. Okay. Now Z is less than R. It was Z is greater than R. Now look at here, in this region, Laplace equation is not satisfied. You can't expect that one. Average of the potential over the surface is equal to potential at the center. You can't expect this one because Laplace equation is not satisfied here. You got charge, isn't it? But if you find that one, now exactly same calculation, am I right? Take one patch of surface area, dA, it is at a R here. So take this one as one more vector. So this is your italic R from source to field point, am I right? Italic R. So exactly everything is same. This is theta. All calculations are same. Now if you find potential average, what you get here is 1 by 4 phi epsilon naught, you will get Q by capital R. Why? Look at here. When you write R minus Z here, Z will be 2Z. Z will add up 2Z. R will not get cancelled. 2Z will get cancelled. 1 by R will remain. Just try to show that one. Is that okay? So now we can extend this argument because potential will follow kind of additive rule. So average of the potential over a sphere of radius capital R 1 by 4 phi epsilon naught Q enclosed divided by R. This was the charge inside, am I right? Now I am going to extend that one. Q enclosed divided by R. Is that okay? Now wait a second, there are no other charges, that's my assumption. No other charges. Okay? No other charges. So again, this is again average potential, average of potential due to charges inside, due to charges which are inside the sphere. Okay, only due to charges inside. If you take charges outside, they will follow those rules. Okay, now look at here. Can you just give me again? His statement is not perfect here. Electrodynamics. Okay, average due to charge, or let me write like this. Okay, V average due to charge inside 1/4π/0 Q enclosed by R. R is the sphere that we are talking about. Okay, inside the sphere there are these many charges. Okay, first one. So second one is again, now actually whatever the formula he tried to define is average of the potential due to all charges. Average of the potential due to all charges inside and outside is equal to average of the potential, wait a second, that's equal to potential at center due to outside charges. Wait a second, if there is no charges inside, this equality is valid. We don't have to edit this one. Look at that one. Look at that one and think over it. Wait a second. Potential due to all charges outside the surface should be equal to potential at center due to outside charges. But I have charges inside as well as outside in this situation. Outside charges will do like this. Outside charges will average out. It will give like this. Inside charges average it will give like this. Plus, so 1/4π/0 charge enclosed by R, or I better to write in V. What is that one? Average due to charges inside. Try to understand this statement. This asked someone. Any question? All charges inside and outside, that's equal to potential at center. Obviously, due to outside charges. Outside charges will follow that rule. Average will be equal to potential at the center. But inside charges, they will contribute this part. Now, if you take a gradient, this part will be 0. Okay? So, if you try to relate electric field, so it is surprisingly. So, average of the electric field due to all charges outside and inside, that's equal to, electric field at the center. So, that is problem number 3.4. Okay? Problem number 3.4. I think he might have argued in a different way, but to take a gradient here. Okay. So 3.4 says, show that average of the electric field over a spherical surface due to the charges outside the sphere is same as the field at the center. What is the average of the electric field due to the inside charges? Yeah. What is the electric field? What is the average of the electric field due to inside the charges? Inside charges. That should be 0 because average of the potential is constant. Constant, look at here. Okay, try to understand this one, okay? I mean, you don't have to, again, do all of this mathematics. You just have to understand this statement, read it again, okay? So 3.1 and 3.4. Is that okay? Let me again explain later. Now, problem number 3.2, have a note on problem number 3.2. He calls that one as Earnshaw's theorem. Charged particle cannot be held at stable equilibrium position using only electrostatic force. It's very hard to believe, am I right? Suppose if I have charges on the corners of the cube, you may feel like I can place one charge at rest at the center, isn't it? But at that center, maybe your force is 0. Net force is 0. But that is not a minima of the potential. Is it okay? In the region where Laplace equation is satisfied, potential will never have maxima or minima. Is that okay? So that's why you can't have stable equilibrium using only electrostatic force alone. Is that okay? That will be the practical problem. Just read out this problem number 3.2. Have a note on that one. They will use both electric field and magnetic field to trap any charge. It's very difficult to trap any charge. Is that okay? Ions. If you try to trap any ion, it's very difficult, remember. Not electrostatic force will allow us to do that one. Okay, that's a proof here. Since potential suffers no local maxima or minima, you can't keep any charge at rest. Charge will be rest means that's only happens in case of stable equilibrium, am I right? Charge at rest means, I mean, when a charge can come to rest, if you try to displace it, if it tries to go back to that one. Just like our minima of our spring potential, isn't it? If you try to displace, it will try to go to its mean position. If it happens only, that is the stable equilibrium position. Is that okay? That will never happen in case of potential in the region where Laplace equation is satisfied. Is that okay? So once you define for potential, same thing will happen for potential energy. Multiply by charge, you will get potential energy, am I right? Potential multiplied by charge, you will get potential energy. So if there is no potential minima, you can't keep the charge at rest actually. Okay, that is the theorem. Just read out this one. Do problem number 3.3. A part of this problem is asked somewhere, okay? 3.3. Solution of Laplace equation by assuming potential difference depends only on R in spherical polar coordinate, by assuming potential difference depends only on S in cylindrical coordinate. That will be once potential depends on only one variable, that will be ordinary differential equation. Okay? So solve that one. Find the general solution. I mean, you will have integration constant. Okay? Find the general solution. So take a quick break. Yeah. Saddle point. Yeah, it can have saddle point. It can have saddle point. No, but it said no extremum, am I right? No, saddle point is not extreme value. Saddle point can happen. Extreme value means maximum possible value, minimum possible value. Isn't it? Yeah, let me think over it, because we haven't taken complete proof, remember. We started with one dimension. We just proceeded to 3 dimensions. by just stating. Okay. So yeah, let me comment on it. Saddle point. What do we do with the saddle point? So just to get all ideas about this problem, 3.1, 3.2, 3.3, 3.4. Okay. 1, 2, 3, 4. Yeah. So take a break. Let me continue. Yeah, never. It will never have minima or maximum. Let me comment on saddle point. I have to think about it. Okay. So that's very hard to believe. But remember, there are questions I think asked in TIFR and in I don't know, in CSIR. He will ask, suppose a charge is confined to the plane or a straight line. If you are forcing that one to confine, then sometimes you can have potential minima. But in case of 3-dimension, it will never. In practical situation, it will never happen. So there are some problems. Let me grab that one. I think in YK-LIM. Okay. They have asked in TIFR. Find the frequency of small oscillation of the charge. They will give some charge distribution, and what will you get is from at one point you will get potential minima, or at one point you can derive equation like this: F is equal to minus kx. That's the main thing. Am I right? You can derive this. You can find the force, net force. You can approximate, and you can find this one. We shall solve a couple of problems on this one. But in that kind of problem, only that is restricted to one straight line or something. Okay, that kind of problem exists where they talk about small oscillation, about some point, about a point where force vanishes. But what I say is, in 3-dimension, it will never happen. That's why Griffiths haven't given that kind of problem. Okay, those are design problems where charges are. Suppose let me give the problem quickly. Let me design the problem. I have Q, 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 Q. Side is A. Okay. Now I am going to place one charge, test charge Q at the center. Now that test charge, it is allowed to move. That is, let me take these are negative. This test charge is positive. Okay, it is at the center. It is allowed to move only perpendicular to the plane containing these charges. When you try to move this charge above, what will happen? These negative charges will attract. Is that okay? And it will try to come back. But this problem is possible only when it moves along straight line. If you are talking only about a line which is perpendicular to the plane, now can you just find what is the frequency of small oscillation of that Q? Is that okay? Side A, minus Q charges, capital Q charge. Find the frequency of small oscillation of this capital Q. Is that capital Q is allowed to move only along straight line which is perpendicular to this plane. Okay, this kind of problem that they have designed, but don't get confusion with this one. Here it is restricted to move along a straight line. Again, to restrict you need some other force, isn't it? Other than electrostatic force. So that's why only electrostatic force alone cannot restrict the charge at rest actually. Here also you will feel if I put the charge at the middle point, net force is 0, it is at rest. It will not move anywhere, it will not go anywhere, isn't it? It will escape from some point. Is that okay? Or you can, you have to play with some simulations from internet. Is that okay? There are some many simulations. You can keep charges and you can keep one more charge which will move. I think best one is GeoGebra. Okay, GeoGebra simulation. Just search for that. Okay, or PHET simulations on charges. Okay, you can play with that one. So it will never be at rest. It will, what you call, slide off from some point. Okay. Now take it as a question, not charge, okay? So if the charge is restricted to move in on a line which is perpendicular to the plane of those charges, is that okay? Then what is the frequency of small oscillation? Okay, try that one. Let me give you the right question, okay, later. Or I think before trying this one, you better try this one. Now it is allowed to move only along straight line. Okay, it's allowed to move only along straight line. Yeah, try to do this one. Okay, here it force is 0, you know that one. But in 3 dimension, if you have this kind of structure, it will escape from some point, remember. Is that okay? So, or it will fall down to one of the negative charges. It will never be stable. So, but if you restrict one-dimensional motion, you can have small oscillation. So, try to find frequency of small oscillation. So, try to do this one, okay? Not this one. Let me just check it out, okay? Because when you displace this one, it's, I think it's very difficult to define net force actually. Is that it? But I think you can try. You can try. Okay, try that. First do this one. When you displace at a distance x from this middle point, what is the force? I mean, find that force when you displace that one, and take the displacement as very small, and do some binomial expansion, whatever you can do, and show, get this kind of equation. That's it. This k will decide frequency of small oscillation. Okay. So try that one. Let me grab the right question.